All right, so now after all of the work we did yesterday, looking at the integrals of sines and cosines, we're going to switch our attention to tangents and secants. Okay, so before we do that, what I've done here is gathered up a list of formulas that we will find very useful in this section. Hold on one second. Okay, so in other words, if you can see here, I've got integrals for the secant squared of x, secant tangent of x, the tangent of x, and the secant of x. Also on the next slide, I've got two derivatives that will also come in handy. We'll need these throughout this section. They're, of course, in the tables in the back of the book. And just quickly remind you, if you look back here, yes, they're all here. So these are all the trig integrals. Oh, they've got everything here. Yeah, everything you can look for. Anyway, so we're going to start by looking at two different cases. So usually with these trig integrals, we're trying to organize these problems into different categories because the exponents are what really determines which techniques we should be using. Now, usually there's more than one way of going about these integrals, but there's often a quickest way. And so what we want to do is find that quickest way by focusing our attention on the exponents that we'll be using. So we'll start with the first case, the secant raised to some j power x times tangent of x. So here's our first example. Now we can see here, and this is, by the way, this is where these formulas start to help. And also, I just want to remind you of the Pythagorean identities, which we're finding are very, very helpful. I think that I put that in here somewhere. Let me just go grab them again. We've got so much stuff in here. I hope I did. There they are. Okay, great. So what I'm going to do is copy these onto a new sheet or slide so we don't have to keep scrolling back and forth. And you'll see why in a second, why we need this. I'll put them right here. By the way, I added an appendix to this chapter. I just want to mention it while I'm thinking about it, in which I actually am going to demonstrate why these Pythagorean relationships actually hold. In other words, we've been talking about them, but I want to show you why they are true. First, though, we'll use them for these different integrals, and then at the end, we can stop and say, well, listen, why don't we go back and demonstrate why these relationships hold? It's kind of interesting. It turns out that they're basically based, I mean, they're ultimately based on geometry because, of course, the Pythagorean theorem is based on a right triangle. And so, of course, it stands to reason that these will be as well. All right. So here's the Pythagorean identities that we'll be needing. And of course, in this section, the ones we'll be, this is the one we're really interested in this section. Secant squared x equals 1 plus tangent squared x. Why is that important? Because what we'll often be able to do is take an existing integral and rewrite it in terms of a simpler expression by making substitutions. So let me show you how that would work in this first one. So we've got the secant to the fifth power and the tangent to the first power. So if we scroll back, you can see that we have the ability to take the secant squared and convert it into a function of the tangent. And that gives us a hint as to what we're about to do. Okay, so let me sneak this in here. Okay, so what are we going to do here? Well, here's what we'll do. First of all, we'll rewrite this as secant 4 of x, the fourth power of secant, times secant of x, times tangent of x. Well, now, Why are we doing this? Because if you recall from the derivatives that I just showed you, let's take a look at that list. The derivative of the secant is secant x tangent x. Now if you notice, we have that right here. So in this particular case, we may not even need to bother with the Pythagorean identities, because here's what we can do. We can use U substitution very quickly and easily, surprisingly easily. Why don't we try this? Let's have U equal the secant of x. And therefore, U dx is secant x tan x, as we just saw earlier. So that means we can rewrite this as du equals the secant of x times the tangent of x dx. So what do we have here? We've got u to the fourth du. Oh, and that's so easy to solve for. Okay, and that's exactly what we have. U to the fourth du. So this is u to the fourth. This is du. And so we end up with u to the fifth over 5 plus c. And of course, since we define u to be the secant of x, then that means what we ultimately end up with is the secant to the fifth power of x over 5 plus c. Well, all right then. Now that was a very straightforward case. Okay, but it isn't always quite that simple. In the next case, you'll see that we do in fact need that Pythagorean identity. And so every case is different. So here, for example, if you notice, the exponent of tangent is 1. So if we just have a secant and raise to any power we want, and the tangent just raised to the first power, the approach we just used will work just fine. It's just a question of rewriting it slightly so that we can take advantage of U substitution. Again, the reason why this works is because of what you're seeing right here. This is the key to the whole thing. Without that, we'd have to try something different. Okay, so I'll put this down here too as a reminder. And that's how we got our solution. Now here, though, things are changing because all of a sudden the tangent can have an exponent other than 1. So what we're going to do here, if you notice, it says here j has to be even. So in other words, it could be secant squared, secant to the fourth, secant to the sixth. Ultimately, what we're going to do is use this expression in place of this. Okay, so let's see how that works. So let's try tangent to the sixth power, secant to the fourth power. So again, and what this implies is that 1 plus tangent squared of x squared must therefore equal secant to the fourth of x. So that might be a clever way to simplify this. But nothing's guaranteed. I mean, it's possible that we're going down the wrong path here. And, you know, the thing about these trig integrals is until you've had a ton of practices, it's easy to do that. It's, you know, you have to get practice thinking about what makes sense here, what kind of substitutions will work. So, but here we are, in fact, going down the right path, except for one thing. Okay, what we're going to do is this. We're not going to deal directly with secant to the fourth power. Okay, so we're only going to replace one of these secant squares with the Pythagorean identity. Why are we doing that? Well, all right, let's go back and look at the derivatives that I showed you a second ago. Here's a clue. The derivative of tangent of x is secant squared of x. So that means when we rewrite this integral, we're going to want to have a secant squared of x in there somewhere to act as the du when we use u substitution. Okay, now the way it's written here, it's a little bit messy. Let me change it slightly. All right, so I'm going to rearrange it to so now look what we can do. Okay, so look what we can do now. This is now u to the sixth times 1 plus u squared. And all of this now becomes du. So we multiply this out. And then we can split it up into two terms. Well, now we know how this works. Ultimately, it reduces to tangent to the seventh power of x over 7 plus tangent to the ninth power of x over 9 plus the constant. Okay, so that is how this one works. Now, how would you know to do this? Well, again, keep in mind, if you look at these derivatives carefully, and you know how u substitution works, we need a du in there somewhere. So you might look at it and say, well, we do have a secant squared in here. Why don't we try letting u be some function of tangent of x? And then see how that goes. But before we do that, we have to simplify it a little bit more than that, because we actually have secant to the fourth power. So that means we have to do something with this secant. We're going to break this up into two secant squares. So this first part, this here, can become our du. The secant squared of x can be replaced with the 1 plus tangent squared of x because of the Pythagorean identity. So you, by setting it up this way, you can turn it into a very straightforward u substitution problem. Wow. So anyway, but if you didn't go that path, you probably would have wound up with a bigger mess than you started out with. And that's how you would have known that maybe we should try something different. All right. So now how about this one? So instead of having same thing, tangent to some power k, secant to some power j. Here, j is even. So we can take advantage of the Pythagorean identity. But what if, now here actually, what we're worried about here is that secant, the exponent of secant can be anything, but the tangent is k. And we're going to assume that it's odd. Oh, so what we're going to need to do is rewrite this in terms of even exponents. You just saw that this works best, what we're doing when we have some even exponent for each tangent and secant. So let's say we have something like this instead. There's no reason why we couldn't rewrite this as okay. So now what we can also do And keep in mind, there's always a chance that we might need one of these Pythagorean identities. These are written in terms of squares. So here's a possibility. And then what do we do now? All right, let's try this. So this second tan squared x is going to be replaced with secant squared x minus 1. Well, now it does look like we're getting into a lot of trouble here, doesn't it? But not really. Let's see, what are we doing? Ultimately, what we're after is, if you recall from the derivatives that we had earlier, the derivative of the tangent is equal to secant squared of x. So remember, we're really ultimately building up to a pretty complicated u substitution. So let's see, what can we do with this? Oh, man. Oh, also, don't forget that the derivative of the cosecant, the secant rather, from way, way back up here. Way up here. Okay. I'll put that right here. So here's what we're probably going to have to do. We may have to try u equals tangent x, and then again try u equals secant x. One of them is probably the one we want. It's just a question of which one makes this a little bit neater. So I'll tell you what. Let's try this. First of all, let's rewrite this catastrophe. I'm going to try to get all the like terms together. There's not enough room. It's such a mess. Hold on. So suppose that we decide to try u equals secant x. And so remember, the derivative of secant x is secant x tangent x. So let's rewrite it. And so we do have our du. Now, unfortunately, we still have this tangent squared here. We need basically to get rid of everything here that is not a secant. What we can do is go back to our Pythagorean identity. And so basically, what we probably would like to do here all right, now we can substitute our u. By the way, this one, you can see here what we have here is secant squared x minus 1, the entire expression squared. So now it's getting a little clearer what we're supposed to do here, I think. So let me just write that down one more time. It's secant squared x minus 1 squared. Secant squared x. Secant x tangent x dx. Now we can use u substitution. Okay, well now we're getting somewhere. Okay, yeah, there's a lot of algebra coming up, but we can handle this. So first things first, let's see what to do. U squared minus 1 squared. We can do this with FOIL. And so this is I. And then this is last, 1. When you consolidate all these, you get u to the 4th minus 2u squared plus 1. Now, all of that takes the place of this term. Okay, so let me do that on the next slide. This is one of the disadvantages of doing this online. If I had a whiteboard in front of me, I could write like crazy, but I have to obviously stick to the room that I have here. Okay, so after applying FOIL to the term in parentheses, I can just now distribute this u squared across all of these terms. And now integrate. And now just replace. Remember, originally we saw that u is equal to secant x. Oops, that's to the 5th. And after all that, we're finally done. Now, way back here, we decided to let u equal to secant. What if we'd chosen the tangent? Well, we're not going to spend the time doing it right now, but my suspicion is that we would have ended up with something that couldn't be reduced properly. Would have been something missing that we needed. So you would have eventually realized that something wasn't right. I don't think, I mean, other than that, I don't think there's anything else that would give you a hint that this should have been u equals secant x, except the fact that you do have secant tan x, which you do need for du. With the tangent, the du would have required secant squared, which we do have. But then the problem with that is that we would have had this extra tangent x here, which we could not have simplified with the Pythagorean identity. The Pythagorean identities only apply to squared terms. So I think that's where you would have gotten tripped up. If you tried to use tangent here, du would have been secant squared x dx, which we do have, but then that tangent right here would have had no place to go, so to speak. And that would have been a hint that we did something wrong. So yeah, these are really getting way up there in the complexity level. But yeah, it's obviously some of these topics we're covering are going to be messier than others, but it's all important. And it's also just good practice when you come right down to it. All right, now, the third section of this part is the so-called reduction formulas. So we've seen the integrals of sines and cosines. We've seen the integrals of tangents and secants. What's going on here is that you're really just trying to find strategies to simplify what you're doing. Okay, that's really all you're doing. Now, it turns out the book has helpfully for us derived formulas which you can actually throw directly into your calculations. I don't think anyone expects you to memorize these because they're terribly complicated. But what they are helping us do is come up with a general formula for the secant to any power of n and the tangent to any power of n. And that could come in handy, especially if you're dealing with a very messy case. So, but notice that these do not apply when there's multiplication going on. In other words, it can't be something like secant squared, tangent squared. It's just secant by itself, tangent by itself. So let me show you what I'm talking about here. So for the first one, now that's what you call a messy formula. In fact, it leads us to another integral, which you might say, well, aren't we running around in circles and making things worse? No, because by reducing the exponent, at some point we'll reach a point where we can either use a one of the Pythagorean identities or possibly one of the double angle formulas to simplify what we're doing, and that eventually we'll be able to use u substitution, which is, of course, our ultimate aim. And then the tangent has a similar horribly messy formula. Okay, so let's try this out on secant cubed of x. By the way, this is not to say that this is the only way to do this. Okay, but it's a way that we can do this. So for example, using the formula that I just showed you, this means that n equals 3. So this is the general formula. Then we plug in 3 for all the n's, and we end up with this expression. And we do have a formula for the integral of secant x. And so we plug that in. It's in the book, of course. It's the natural log of secant x plus tangent x plus c. And so that would be, it goes in here. Then we have the 1/2. And then this is our final answer. Now, this probably would have been a real nightmare to do it directly. Having that formula could actually be very helpful in these cases. And now we're going to do one with the tangent, that special tangent formula that I just showed you. Again, it's possible we could have done this directly with other techniques, but we're going to use the formula just to see how it works. Tangent to the fourth power x, there's no secants involved or anything else. So we'll go grab that formula that we just had, and noting that n equals 4. So we plug in, we place all the n's with 4s. So we've got what you're seeing here. Now, what do we do with this? Oh boy. Well, we probably, you know what we can do? We can apply that formula to this term as well. In other words, this formula that we started out with, which we applied to tangent to the fourth power of x, can be applied again to the tangent square of x. So we're using the formula twice this time. Oh my God, except that this time n is equal to 2. And so what this is saying that is that when you're done, all of this, as you can see from the bottom, equals the tangent of x minus x. Oops. And then this stays, so you just bring this together with this, and there's your final answer. Okay, so here we are, we brought it all together. We have 1/3 tangent cubed of x minus tan x plus c. Oh my God. So now we're going to take a bit of a brief detour. I just want to quickly show you the logic behind the Pythagorean identities. This is something you don't have, you're not responsible for remembering this. It's just, but I think it's helpful for you to know what's going on behind the scenes with these Pythagorean identities and why they work the way they do. So I stuck this, I call this Appendix 3B. So this one can be derived with geometry, as you could probably imagine, because it's taken from the Pythagorean theorem, which you recall is based on a right triangle. With the two sides A and B, we have the hypotenuse C. And of course, the Pythagorean theorem tells us that A squared plus B squared equals C squared. So everything in ancient Greece was done with geometry. Algebra hadn't really been invented. Well, at least it wasn't being widely used just yet when the Greeks were writing, when Pythagoras was alive. Pretty much all math was done with geometry. I mean, as far as they were concerned, math was geometry. There wasn't really anything else. That the algebra that we know and love came much later. So everything was proved in terms of geometry. Anyway, so that's the one we want to think about. Where did it come from? These other two actually are simply algebraic rearrangements of this first one. We'll get to that in a minute. But first, here's the setup that we need to look at. Here's what we've done. This is what you call a unit circle. You have the 4 quadrants, as you can see. This is the origin. So what we're doing is circumscribing a triangle, a right triangle, into the circle. Now, the important detail here is this. This red line is the radius of the circle. In other words, remember what radius means. You start at the center of the circle and reach out to touch any side, anywhere on that side. That is the radius. It's the same for every one of these. In other words, I could draw a bunch of these, and they're all going to have the same radius, which is 1. That's why we call it the unit circle. It has a radius of 1. Now, we're looking at angle T. So remember, sine is opposite over hypotenuse, and the cosine is adjacent over hypotenuse. So with angle T, this is the adjacent side. This is the opposite side. Oops. And this is the hypotenuse. So from the perspective of angle T, the sine, the opposite over the hypotenuse, is the ratio of this line segment to the hypotenuse, but that's just one. So the height of this blue line, which is the y coordinate of this point, is the sine of T. Okay, in other words, this point tells me where the radius touches the circle. So y itself is the cosine of T. I'm sorry, it's the sine of T. And based on similar reasoning, since the cosine is the adjacent over the hypotenuse, that would be this side, which means that's the x coordinate. We're divided by the hypotenuse, which is just one. So what that means is that this x is itself simply the cosine of T. So in other words, this line segment is the cosine of T. And this line segment is the sine of T. And since this is a right triangle, if you think of the cosine as side A and the sine as side B, and the hypotenuse is C, A squared plus B squared equals C squared, implies that cosine squared of T plus sine squared of T equals 1, because that the radius squared is just 1. And there you are. And the same thing is going to be true no matter what angle T is. I could put that red line anywhere. I can move it up here, for example. And I'll get the same exact result. No matter where T is, this relationship will always hold. Because wherever I touch, that's going to be the XY coordinates, the cosine. Let's say this is, I'll call this angle R. No, not R, because that's the radius. I'll call it angle K. That means right here is cosine of K and the sine of K. Okay, so in other words, this relationship holds for every angle we can have. So therefore, this is true for all angles. And so we ultimately write this as sine squared theta plus cosine squared theta equals 1. Once we get that established, the other two, like I said, are simply algebraic rearrangements. If we continue to use T as our variable, here we're just, if we divide both sides by cosine squared of T, what do we get? Well, this one is just 1. And recall this is equal to the tangent. And then this, the inverse of the cosine is the secant. Okay, so that accounts for the second identity. And then the third one, instead of dividing across by cosine, we'll divide it across by the sine, squared that is. So now this is the inverse of the tangent. Which is just the cotangent. This is 1. And then the inverse of the sine is the cosine. A cosecant, rather. All right, and that's it. We're done with that. So now you know why these three relationships actually hold for every angle. All right, now before we go on to the next topic, which is trig substitution, we need some practice. We're going to do some examples here. All right. And in each case, we might employ a slightly different strategy. For example, let's take a look at this one. Okay, now, as you've seen already, there's several things we could potentially try. Luckily for us, oh, that's right. Why don't we try this before we reduce this to sine squared times sine or something like that? That would probably work well if we had tangents or cotangents or something, but let's just do something simple. Sometimes the simplest approach is the right one. Oh, look at this. Well, that turned out rather well. Okay, so sometimes, give it a shot. If you think that there's a potentially simple way of going about this, try it and see what happens. If you end up with a messier expression, that means you know something's wrong. But if you were able to simplify it, in this case, we really simplified it, and so we're done. That's it. Oh, I wish I could say the same thing about this next one. Yeah, this one's going to take a while. So let's see what we can do with it. It's one of these. Now, this one has an extra wrinkle to it that we'll discover as we go along. And that wrinkle is that these are not tangents and secants of x, but 2x. So here's what we have to watch out for. What if we have something like this? Oh no, we're going to need the chain rule now. Oh boy, so this is something we haven't seen up to this point. Trig functions that require us to use the chain rule. And so in this case, if we're looking at the tangent of 5x, we're going to treat g of x as 5x. You can see this is a composite function. And recall the way that works is that the derivative is f prime of g of x, g prime of x. So now the derivative of the tangent is this secant squared. So it's the secant squared of the original g of x times the derivative of g of x. So g prime of x is just 5. Okay. So here we have f of x, f of g of x is tangent of 5x. F prime of g of x means the secant squared of 5x, but then we need the derivative of this 5x, which is 5. Or sometimes you see it just written like this, just to make it a little neater. It's the same thing, of course. And then, of course, so we ultimately end up with 5c can't square, sorry, of 5x. And based on the same reasoning, remember the derivative of the secant is secant times tangent x. And so we do need the 2 down there because that's the derivative of 2x. Okay. So I just want to point that out before we get any further into this problem, because that we won't really need to worry about that until we get to the very end. In the beginning, we have to think about how do we manage a case like this. So you saw that in many cases when we have odd exponents, because we want to ultimately use the Pythagorean identities, if we can, what we'll probably end up doing is taking this tangent to the 5th power and rewriting it as tangent times tangent to the 4th. All right, so let's do that. Oh, I did something I shouldn't have. Okay, so let's do that. No, I don't think I have quite enough room there. I thought I'd save a little space, but I don't think so. Okay, now what are we supposed to do? All right, well, keep in mind the derivative of the tangent, just the tangent of x, not a function of x, is secant squared of x. So, why don't we try this? Oh, you know what else? Well, all right, we know that. And then just in case we need it, that could help us figure out what to do about or use substitution. So why don't we do this? One of our favorite Pythagorean identities tells us this. So here's what we could probably do. Tangent to the 4th is the square of this expression. So let's see if that helps. Oh, you know what? I just realized this is true right here, but we're dealing with 2x. I have to be careful about that. Okay. So in other words, the tangent to the 4th power of 2x is going to be secant squared of 2x minus 1 all squared. We're squaring the Pythagorean identity because we have tangent to the 4th power rather than tangent squared. And we also still have the tangent 2x. All right, so let's see what we can do with this. And as we just saw a few minutes ago, we need that too because of the chain rule. We don't have that, so we're going to have to provide it ourselves. So let's do that. And while we're at it, why don't we make another change here? Well, first, all right, let's not do two things at once. Let's be careful here. I'm going to multiply the outside of this expression by a half. Now we can do some rearranging. Actually, here's what we're going to need to do. We need a secant and a tangent. So what I'm going to do is take the secant squared. Actually, all right, I'll do this in the next step. Right now, I'm just rearranging. What I'm thinking about doing here is rewriting secant squared of x as secant times secant. Here's why. Because now all of this is our du. Yeah, that's really the challenge, is putting together the du that we need. So what do we have here? So we have u squared. Remember, u is just the secant. Okay. And now when we get to this point, you can see we're almost home. So u squared, let's just get this out of the way. We can apply FOIL. U to the fourth minus u squared. Whoops, that's inner. These two are last. So that comes over here. And now I can multiply through by that u. Break it up into individual terms or individual integrals. Oh, sorry, I missed the u here. That was close. All right, now we apply, of course, our normal rules of integration, so-called power rule. And we can get rid of that too. We can just apply that across. And remember, originally the u was just simply secant 2x. Well, I think we didn't think that one would ever be over. And yet, here it is. Okay. So there's a lot going on in this problem. But I think it's important that we had the opportunity to see how the chain rule works with trig functions, because we haven't really done that up to this point. All right. So I've got several more of these that I want to go over, but not today. And when that's done, we can dive into the next section, which is trig integration. Now, trig substitution, I should say. What you're doing there is you're basically taking a very messy integral and you're replacing some components of it with an equivalent trig expression to make things a little bit simpler. The only motivation for doing any of this is to simplify problems that we're working on. So everything we're doing here will directly follow into the next section, where we won't actually have trig functions directly in front of us. What we're going to try to do is create them algebraically from the existing integrals that we have, so that we can now go ahead and follow these same procedures. Anyway, so something to look forward to. So I'll see you all next time.